Hi, I am Dr. Goodmanson. In this video, I am going to check out the latest version of Surfaces. Version 2.9 is soon to be released, and I am going to demonstrate some of the new features offered in the program. There's a while since the last version of the program, version 2.8, was released. It turns out it has been in steady, albeit periodic development, and there are substantial changes to report. These can be put into two classes: major changes and polishing. I will present these in no special order. The first one exemplifies polishing, but is handy nonetheless. The size and position of the program window can be stored and then recalled at a later time. You can also enter the desired window size for this purpose. This is a handy feature for getting identically sized screen captures for presentations. Let's start a new project. The worksheet in the new version now opens with typical and frequently used groups pre-created for the user. Now let's create a surface to show other new features. Let's first insert a rectangle and then stitch a surface to it. As in the previous versions, pressing and holding the Shift key allows the program to search for likely vectors to stitch the surface to, and by clicking the left mouse button to confirm, the surface is quickly created. Now here is a feature that should be helpful to all beginning users of the program. Select Tools, Options, and then select the VLM tab. Place a check mark next to the check and display surfaces whose A1 or A2 curves are not parallel to the x-axis. This forces the program to check the alignment of vectors used for surfaces. It is a common mistake among beginners to violate this quasi-requirement. It is quasi because it can cause a piercing vortex error and prevent a solution to be generated, but may be necessary to better simulate the aircraft, for instance when implementing a wing incidence or washout. In other words, it is okay to have the vectors misaligned within reason, but as a rule of thumb, most A1 and A2 vectors should be parallel to the x-axis. This option is generally turned off by expert users. Next, let's add an airfoil to the A1 and A2 vectors to demonstrate another new feature. Let's select a NACA 23018 airfoil for the root. And 23010 for the tip. Now look at these 2 points. They are called control points. They were generated automatically when we changed the A1, A2 vectors into parametric curves for the airfoils. Let's display their IDs. You can see that the root vector uses 0.5 as a control point, while the tip vector uses 0.6. When we open the properties form for the surface, we see a new option. Ensure control point is normal to A1 and A2. To understand what these do, let's first show how this was implemented in earlier versions of surfaces. It was left to the user to enforce the proper alignment of control points. For wings with airfoils, this almost always means that the control point is normal to the surface plane. For demonstrations, let's uncheck these and look at our surface in the YC plane. Say we want to rotate the tip about the root vector, and that we ignore to select the control point. Select Modify Rotate Points form. Select the root point to rotate about. As expected, its Y and Z values are both 0. Then let's enter, say, 15 degrees of rotation as if we wanted a ginormous dihedral. Press Apply. See what happens. The program does what we told it to. Our mistake is that the control point is no longer normal to the wing plane. You can see that the tip airfoil is not slanted with respect to the wing plane. We have decambered the airfoil, modifying its properties. The same actually holds for the root airfoil. It too is no longer normal to the wing plane. It too is decambered. This is a very common mistake I see my students make all the time. Now I can demo the new feature. Let's reopen the properties form for the surface and check the new options. This forces the control points to always stay normal to the surface. When we press the OK button, the program regenerates the model, forcing the control points to be normal. Their distance above the wing plane equals the chord length. Now let's check out another new feature. When making jet aircraft with external podded engines, it is normal to use two approaches. One, a simple cruciform nacelle like you see here, and two, a more complicated hoop nacelle like you see here. The latter one is tempting because it improves the appearance of the model. However, the orientation of the surfaces is critical to proper implementation. When the nacelle is at an angle of attack, all its panels should be generating an upward pointed force. When the nacelle is at a non-zero angle of yaw, its panels should develop sideways force that is properly aligned with the airstream. Therefore, making a hoop nacelle is a little bit tricky. Surfaces now comes with a new tool to make this easier. It allows circular hoops to be automatically generated. Let's modify its nacelles to the new form. Here we see the nacelle is of the simpler kind. Let's delete the vertical wall. Then let's split the B1 and B2 vectors. Then delete the horizontal surface. Reconnect the input vector to the new center points. And delete the input vectors and points. Then convert the output vector into a nacelle airfoil. Here, assume it can be described by a NACA 21008 airfoil. Then go to the three-dimensional view and let's transform this into a nacelle. Open the Insert Circular Surface form. Let's give this a name. Press the pick button and select the rotation axis and curve to rotate. Let's change the number of chordwise panels to 6 and press the OK button. Voila, a nacelle has been born. Next, let's check out a new alignment feature. First, let's drop a bunch of points here behind the airplane. If you're a regular user of surfaces, you may be familiar with the alignment tool. To demo, let's select these points here, then select Modify Align Points. Start by picking the points between which the point we selected earlier will be aligned. When I press Align, these points will be repositioned along this line. Since this is not the new feature I want to demonstrate, let's undo and introduce the new feature. Go back to the form and select the Align Along Curve tab. You can enter any curve you like. Voila! The points are now aligned along the curve. This is a great tool if you're interested in studying lifting surfaces with nonlinear leading and trailing edges. Now let's go to the three-dimensional view and check out a major feature added to the program. As you know, it is important to be able to present the new design in a positive light. This is generally hard to do in vortex lattice codes because the model is, well, 2.5-dimensional rather than 3-dimensional. This is one reason for the development of the following feature. First, let's add refined airfoils to the wing and horizontal tail, because this new feature requires this. Let's assume the root airfoil is a NACA 23016 and the tip a NACA 23012. Let's copy-paste this to the left wing. Then let's add airfoils to the horizontal, say NACA 0010 for all stations. Now we're ready. See this new icon? Press it to display the model with three-dimensional effects. You note that since the nacelle we added earlier also uses an airfoil, the effect extends to it. It is important to realize that Surfaces does not purport to be a solid modeling software. It is not. It is an aircraft design software with a built-in vortex lattice solver and other tools. Regardless, this feature is probably welcomed by many users as it will allow the designer to better visualize the aircraft. I certainly welcome it for my design studies. Here are some examples. Alrighty then, let's check out some other new features. Several new tools have been added to the program. Here, for instance, is a standard atmosphere calculator that allows the user to check out the properties of the atmosphere up to 278,000 feet or 84 kilometers. This tool is designed to help the user evaluate a proper sizing of wing area. Imagine we're designing an LSA to cruise at 112 ktas at 8,000 feet while meeting the 45 kcas stall limit. The target gross weight is 1,320 pounds, and assume that we expect a clean minimum drag coefficient of 320 drag counts. Aspect ratio is 8.5, and let's estimate the nacelles efficiency using equation 9-89 in the first edition of my book, or equation 9-129 in the second edition. Furthermore, say that we expect the cruise lift-to-drag ratio to be about 9.5. Next, let's bound the problem. It is common to see maximum lift coefficients in this class of aircraft to range between 1.3 and 1.8. The 1.8 is unlikely, to say the least, but it limits the range of lift coefficients. As you will see shortly, this tool will step from CL max of 1.3 to 1.8. The range is 0.5, and thus having 6 steps will make the plot look better. If you're familiar with LSA aircraft, you will agree that a suitable range in wing area is between 100 and 150 square feet. Since this is a range of 50 square feet, let's also use 6 steps here. The next tab displays the result of the analysis in the form of a carpet plot. You can see the horizontal axis represents cruising speed in ktas, and vertical axis represents stalling speed in kcas. The red lines show our target values. Unfortunately, the carpet plot shows that, considering our input values, to meet the cruise speed of 112 ktas target, we should not have a wing area greater than about 109 square feet. However, to meet the 45 kcas stall speed limit requires a CL max close to 1.8, which is next to impossible to achieve without a high lift system. A realistic CL max for this class of aircraft is 1.5. There are exceptions. For instance, the pilot's operating handbook for the Cessna 162 Skycatcher reveals a CL max of 1.68. Anyway, if we assume a CL max of 1.5 for our aircraft, we will need a wing area of about 129 square feet. This will drop our cruising speed from about 112 to 104 ktas or so. This shows we have some decisions to make before we can meet our targets. The next tool is remarkable for the mathematical aircraft designer. Remember that surfaces is a symbolic vortex lattice solver. This of course means substantial power. The symbolic solver can be put to good use using this tool. To demonstrate, let's open a fresh worksheet. Select Tools, Parametric Design Editor tool. Let's open the demonstration file that comes with the program. The editor allows the user to define the aircraft through truly mathematical means. Variables are defined by entering the symbol, followed by a colon and equal sign, and then the expression is entered next. You can see this by pausing and taking a gander at the code. You can ensure that entries are transferred to math objects with the same symbol, and that way creating a model that can be immediately analyzed. Here, let's change the wing aspect ratio to 10 rather than 16, and the aspect ratio of the vertical tail to 1.2 rather than 2. Airfoils are defined using the same parametric curves returned by the camber creator. Then, a simple command is used to create the lifting surface, the create function. Then, when ready, press the OK button. Here, the code creates this system of a wing, horizontal tail, and vertical tail. The tail is a bit awkward, but you get what you program. Next, let's run the solver to see what happens. Yes, the colors indicate the solution was uneventful. Next, let's look at a truly notable tool added to the program. First, let's create a new worksheet. This is the Automatic Aircraft Sizing tool. Remember, while designing aircraft is a highly complicated activity, there are patterns that can be automated without diminishing the whole experience. This tool creates a basic system consisting of a wing, horizontal, and vertical tail. It offers the user to select a conventional, canard, and a flying wing configuration. The first page presents user instructions, so it is vital for the newcomer to read these. The instructions are saved when the form is closed, allowing the user to add own comments. Once a configuration is selected, the tool opens a second page for more details. Some of those include airfoils, weight model, static margin, cruise speed and altitude, weight at condition, and the geometric properties of the lifting surfaces. Then, when ready, press the Create button to form a perfectly assembled vortex lattice model, sized to fit. The tool also places all geometric entities in their proper group so that you don't have to. More importantly, by pressing the Analyze Configuration button, the tool conducts a rudimentary analysis of the model that evaluates its stick-fixed neutral point, places the center of gravity at the appropriate static margin, and trims it for the entered cruise speed, altitude, and weight. Furthermore, the form also offers optimization capabilities. For instance, it optimizes the wing geometry such the entire wing contributes equally to the generation of lift, and thus minimizes lift-induced drag. This optimization accounts for the effect of trim drag. The program also optimizes the twist of your flying wing configuration such it cruises with neutral elevons. Next, let's look at some of the new graphics features. For this purpose, let's open the surfaces model of my radio-controlled FPV Explorer you may have seen in my other videos. Start by viewing the airplane in that three-dimensional view. Here, let's change the isometric view to the more realistic perspective view. It can be accessed from the Tools menu and this drop-down menu. Let's select the Three-Dimensional Effects tab. In the three-dimensional view, Surfaces transforms the vortex lattice geometry into three-dimensional triangles to better approximate the intended geometry. The panel presentation frame provides control over which edges of the triangles are displayed. The 3D display quality frame provides control over how many triangles are created to represent the model. The higher value increases the number of triangles, improving quality, but may affect display update rate. The source of light frame provides control over whether the light illuminating the model is always at the viewpoint or is fixed in space. Let's return to the workspace. Clicking the 3D icon will toggle the three-dimensional triangle and vortex panel views on or off. This also shows the various edge display options. The edge colors can be modified as well. Next, let's look at some other new features. The grid appearance has been improved. The user can also modify the appearance of the legend. Searching for variables has been improved as well. For instance, say we're searching for the math object containing the x position of the center of gravity. Type capital X, lowercase c, g, and hit enter to store it in a drop-down list. Say we also want to get access to the Cm alpha, Cl beta, and Cn beta derivatives. Then type CMA and hit enter, CLB and hit enter, and CNB and hit enter. Now we can quickly go from one to the next rather than having to scroll the list up and down looking for them. The list can be cleared as shown. If you have used Surfaces before, you probably noticed the graphics theme is different and the workspace background color changes from top to bottom. Let's open the Options form to see what has changed in regards to the appearance of the workspace. The Legends fore and aft colors are controlled here. You can turn the gradient background on or off here. Note how the changes are implemented instantly. To change a color, simply click on the color box and select a new color. Turn on the gradient background and you can change the colors using these color boxes. You can also save the current color scheme in a file called a color scheme. You can read existing color schemes as shown. The program comes with several schemes. If you don't like them, change them to your liking. Here some of these are shown. The orientation of the model in the three-dimensional view can be changed quickly by using the improved 3D presets form. You can view your airplane from above, below, left, right, front, and back, in addition to 4 typical viewpoints. You can also change the orientation by entering directional and azimuth angles directly. Now let's check out another major feature in the program, a 3-view drawing. A 3-view drawing is an essential product of the aircraft designer. Surfaces allows the airplane to be quickly transformed into a 3-view drawing. Right-click in the workspace to open a pop-up menu or select 3-view drawing under the View menu. The program displays the model with all dimension lines turned on in the corresponding worksheet planes and shows a legend containing math objects shown in the list. Two additional matrix solvers are offered, a Gauss-Seidel and a lower-upper decomposition solver. The former offers significant speed improvements, between 4 to 8 times faster. Unfortunately, it is restricted by the properties of the aerodynamic influence coefficient matrix that depends on how the model is made. Sometimes this renders the Gauss-Seidel algorithm unable to converge to a solution, but when it does, well, it makes a huge difference. To demonstrate the difference, let's obtain flow solutions for my design of a small twin-seat LSA class light plane, the SG-1 Explorer. The model to the left uses the standard super robust Gaussian elimination solver. The right uses the Gauss-Seidel solver. This is shown in real time. Using my 5-year-old HP laptop, the left model solution takes 22 seconds to converge. The right one took 6 seconds. The recording of this video slows this down a hair. Without recording, the left one takes 19 seconds and the right one 4 seconds. Note that the solution includes force contributions from thrust, propeller normal force, and tire drags. Next, let's check out improvements in the display of the flow solution. Open the VLM console. Select Results, Plot Streamlines to open the Streamline platform. This tool creates a rake along which Streamlines will start. Specify suitable endpoints for the rake. Here enter 16 points along the rake. Press the Create button. Surfaces goes to work and creates the 16 streamlines requested. Here I deliberately placed the rake near the right wingtip to visualize the wingtip vortex. The streamlines will remain until the user closes the form. Next, select Results, Plot Flow Solution. This opens a form to plot the flow field on a specific plane. Here, for instance, it is insightful to plot the flow field on the YC plane placed a short distance behind the aircraft. Enter suitable size by specifying the extremes of the plane. Here I want 60 points along the y-axis and 20 along the z-axis. The plane will be placed at x equals 5 feet, which plants it aft of the aircraft. Press the Create button to show the solution. Voila! The two plots give a great insight into how the presence of the aircraft affects the flow velocities around the airplane, showing both the wingtip vortex and downwash between the two vortices and upwash outside of the wingtips. Let's turn off the streamlines and plot the flow field as a contour map. This shows the total velocity. This only shows the vertical flow components. Red represents down moving airflow, the blue up moving airflow. The primary improvements in these two tools is that the flow arrows are persistent, allowing the user to reorient the viewpoint for best view. The flow field image remains until the user closes the form. Next, let's demo the virtual wind tunnel. Select the Run the Virtual Wind Tunnel. This opens the wind tunnel form. Let's make the form wider so we can see which other parameters should be entered. Make sure the Replace CL and Replace CD checkboxes are marked. This ensures the wind tunnel run will extract these values from each flow solution. Double-click the Sweep Type cell to open a list of sweep types. Here we are going to perform an alpha sweep. Double-click on the Start and End cells to set the initial and final values for the sweep. Start at -5 degrees, end at 5 degrees. The difference between the two is 10 degrees. Therefore, using 11 runs ensures a list of -5, -4, -3, etc. degrees, rather than having some results fall between integer degrees. This is not a requirement, but makes it easier to interpret results. You can see the AOA cell has 2 degrees in it. Since we selected an alpha sweep, this angle will be ignored, so leave it as is. However, all the other parameters shown will be used as entered during the sweep. Had we selected beta sweep, then the AOI value would be ignored in lieu of the sweep angles generated, and AOA would stay at 2 degrees. Note, the user can perform multiple runs using the tool by adding additional sweeps by pressing the Add or Insert buttons. Press the Start button to begin the wind tunnel runs. This takes you to the next page to allow you to watch progress and perhaps plot specific values. Here we see the AOA in degrees on the horizontal axis and lift to drag ratio on the vertical axis. Here we see the lift coefficient on the horizontal axis and lift-induced drag on the vertical axis. And here we see lift-to-drag ratio plotted against the lift coefficient. Once the program finishes the wind tunnel runs, you can close the form. Surfaces saves the result in a text file using the file name given on the first page. Now let's open it in another tool by selecting Virtual WVT, View Virtual Wind Tunnel Results. The first page of the form shows a list of available wind tunnel runs, in which we find that of the FPV Explorer. Click to select it. This loads the data generated during the wind tunnel run. Click on the Data tab to confirm it was properly read. You can see that substantial amount of data has been collected. Click on the Plot tab to plot the desired data pair. Here, drag versus lift. Select the Options tab to co-plot a curve fit to the data. Here, select the quadratic curve fit. If desired, you can enter numerical format to display with the equation that will be shown in the plot. Go back to the Plot tab to see the second order curve added to the graph and the function that describes it. Click on the Summary tab to see the results extracted, which includes important parameters such as CL-min-D and the maximum lift-to-drag ratio. Note that these results are generated using force integration. Let's plot the lift curve. You can see the lift curve equation in the lower right corner. Press the Calculate button to open the built-in calculator. It has the expression automatically entered. Enter 2 in the variable box and press Enter. The calculator shows you the value of the lift coefficient at an angle of attack of 2 degrees. It is about 0.435, and for 4 degrees it is about 0.622. Press Close to close the form. Next, let's check out the Load Analysis tool. We are interested in evaluating the span-wise shear, bending moment, and torsion acting on the left or right wing. Here, select the right wing. Select Results, Force, and Moment Integrator tool from the VLM console. The Select Surfaces list shows all the surfaces that have been created. The ones belonging to the right wing are checked. Let's set the local coordinate system at 0.0.0. Let's make the view a little cleaner. Then let's visualize the shear force distribution. It is stepwise because the vertical force for each wing slice is being summed up. The graph shows it reaches a maximum of 1.965 pounds at the root. Recall that this is a radio-controlled airplane that weighs 2.57 pounds. The model is untrimmed, which is why this force is so much larger than it should be for 1G flight. This highlights that in order to use the tool correctly, you must first trim the aircraft at condition. Here the wing bending moment is shown. The maximum amounts to 2.192 foot-pounds. Let the program create a curve fit to the bending moment. Here the shape looks like a quadratic function. Now we can inquire about the bending moment at a specific wing station. For instance, at 1/2 foot from the plane of symmetry, it amounts to about 1.32 foot-pounds. Let's close the form and take a look at improvements in plotting dynamic stability. The general procedure for evaluating dynamic stability is to start with the Tasks menu. We always start by determining the stick fixed neutral point. Then we trim the aircraft at condition. This means at the desired airspeed, altitude, weight, and configuration. The last step is to evaluate the stability derivatives for that condition. It is not enough to determine the derivatives for just one angle of attack or airspeed. The stability derivatives change with the angular orientation of the aircraft. Some change a lot, others less. This means that for all intents and purposes, as far as stability derivatives concerns, the airplane at 2 degrees of angle of attack is different from the airplane at 4 degrees. Anyway, once the stability derivatives have been determined, and assuming the moments and products of inertia have been properly determined, the program will simulate fundamental dynamic modes, giving you an indication of how the airplane may handle in flight. Let's look at the simulation of one of these important dynamic modes for the FPV Explorer. First, let's review how this was done in previous versions of surfaces. Make sure you save the airplane model with all vectors of interest visible as the vector wireframe of the airplane is plotted. Then reduce the size of the step console so we can better see the model. Press the rightmost blue icon to run the simulation of the Dutch roll. You can see the airplane's wireframe dancing left, right, left, right. Version 2.9 of the program has improved this quite a bit. To demonstrate, let's select a few points in the workspace and place them into a new group. Call it Streamers. Hide the rest of the points. Next, set up the simulation to create a movie. So next time we press the blue icon, we will be prompted to confirm whether we want to make a movie. Responding with a yes will begin the generation of frames constituting the movie. Next, let's compare this to the real thing. Here's the FPV Explorer in flight. Note that the motion of the drone contributes to the visual effect. Also, despite my best effort at generating a step rudder input, the actual rudder deflection behaves more like a ramp input. Therefore, one should not expect 100% accurate similarities between the real and predicted motion. Rather, a qualitative comparison shows the motion to be reasonably close. See it again. We have now come to the end of this introduction. It is clear that the next version of Surfaces offers substantial changes and improved tools that continue to help the aircraft designer for years to come.